Virtual reality and augmented reality were once distinct technologies. VR, or virtual reality, creates an immersive, closed environment. AR, or augmented reality, overlays digital information onto the real world. By mid 2026, these silos have converged. We now define this unified field as extended reality, or XR. This convergence forms the foundation of modern spatial computing, where digital and physical realities seamlessly integrate into one interactive experience. Spatial computing is now the primary mode for our digital interaction. All extended reality systems function through a fundamental core cycle: input, processing, and output. First, the system senses the environment through cameras and spatial sensors, turning physical data into digital input. The AI then processes this information in real time, mapping the space and understanding the user's context. Finally, the system projects visual output back to the user, closing the loop with immediate, spatially anchored feedback. This loop repeats dozens of times per second, creating the illusion of a seamless digital overlay in our physical world. Devices use simultaneous localization and mapping, or SLAM, to understand your surroundings. By tracking feature points in the environment, the system builds a precise 3D digital map of your physical room in real time. As the headset moves, it continuously scans the geometry of walls, floors, and objects, creating a mesh of nodes that define the space. This mapping process allows the system to anchor virtual objects to specific physical locations. Once anchored, the digital object remains fixed in space, even as you move your head. Virtual reality relies on high-resolution microdisplays. These create an opaque, fully immersive field of view, replacing your surroundings entirely with digital content. Each lens houses a micro LED or OLED array. These tiny pixels emit light directly into the eye, rendering the entire environment. Because the system is opaque, it completely blocks the physical world, allowing the brain to fully accept the digital simulation. Augmented reality hardware functions through two primary display architectures: optical see-through and video pass-through. Optical see-through uses waveguides. Here, light from a digital projector is funneled through transparent glass, allowing the user to view the physical world directly while digital light is injected into their line of sight. In contrast, video pass-through captures the physical environment using external high-fidelity cameras, then reproduces the world on an internal screen positioned directly in front of the user's eyes. While optical methods offer zero-latency real-world vision, video pass-through enables seamless blending of virtual objects with the captured reality, defining modern mixed reality systems. Motion-to-photon latency is the critical delay between a physical head movement and the corresponding update on the headset display. To ensure comfort and prevent motion sickness, modern spatial computing systems must maintain this round-trip latency below 10 milliseconds. If this delay exceeds 10 milliseconds, the sensory mismatch between your inner ear and your visual field creates profound motion sickness. By optimizing this feedback loop, the virtual environment responds instantly to your movements, effectively dissolving the barrier between you and the spatial web. Persistent anchors are the foundation of a shared spatial reality. They allow digital objects to lock into specific physical coordinates. When you place a virtual note on your desk, the system anchors it to the room's geometry. You can leave the room, and the object remains exactly where you left it. Because the anchor is persistent, the note stays firmly fixed in physical space, waiting for your return. By 2026, the era of bulky, uncomfortable head-mounted displays has largely come to an end. We have transitioned to sleek, lightweight smart glasses that mirror the form factor of everyday eyewear. This is made possible by advanced optical waveguides which guide light from a tiny engine into the lenses, allowing for a thin, transparent profile. These devices are now socially acceptable for daily use, blurring the line between physical and digital reality. By mid-2026, large multimodal models are integrated directly into the operating system of spatial headsets. This AI engine constantly interprets your surroundings in real time, recognizing objects and understanding context without the need for manual coding. Instead of explicit commands, the AI anticipates your intent. It knows that when you reach for a document, you likely want to open it, simplifying interaction to a mere glance. This marks a shift from rigid input systems to a fluid, context-aware experience where the digital world feels as intuitive as the physical one. We are moving away from handheld controllers. Instead, the interface of the future is the human eye itself. Foveated rendering uses eye tracking to concentrate processing power only where you are looking. By rendering high-quality visuals at the focal point, we maximize efficiency. By tracking your gaze, the system anticipates your intent. Simply looking at an object can trigger selection, enabling a seamless, controller-free experience. This evolution in spatial computing makes interactions more natural and immersive than ever before. Modern XR hardware adopts a pass-through first architecture. Instead of blocking the world, high-fidelity sensors act as a window. Cameras capture the physical environment in real time, feeding it to the device's internal displays. This enables mixed reality, where digital workflows are anchored directly into your physical workspace. The result is a seamless interface that prioritizes physical awareness alongside digital utility. The internet is evolving from flat pages into the spatial web. Traditional browsing limits us to 2 dimensions on a static screen. OpenXR standards enable a new era of Web 3D. Now, websites exist as volumetric portals, breaking out of the monitor to project directly into your living space. These experiences allow us to interact with data spatially, turning static information into immersive environments that surround the user. The boundary between digital content and physical reality continues to dissolve. In modern industry, extended reality creates what we call digital twins. These are precise virtual replicas of complex physical assets, like engines or entire buildings, synchronized in real time. Engineers use XR to simulate these assets before anything is built physically. Data flows from sensors into the model, allowing for predictive testing. This XR environment acts as a sandbox, where performance data is stress-tested in a virtual space. By identifying failures digitally first, we save significant time and resources in the physical world. Photorealistic telepresence is transforming virtual interaction by creating lifelike, three-dimensional avatars. High-fidelity scanners first capture the geometric mesh of a user, ensuring precise representation of physical form. This data is rendered in real time, allowing participants to feel as though they are physically present in the same shared environment. By matching lighting and textures, these photorealistic avatars make virtual meetings indistinguishable from in-person collaboration. Healthcare professionals are revolutionizing surgery through augmented reality. By overlaying complex MRI and CT scan data directly onto the patient, surgeons gain what is effectively X-ray vision. This spatial data is anchored to the patient's anatomy with sub-millimeter precision. It allows for pinpoint accuracy when navigating sensitive tissues, significantly increasing safety and reducing recovery times. In manufacturing, AR provides real-time step-by-step visual overlays, drastically reducing the cognitive load on workers. By highlighting exact assembly points, factories achieve a 40% reduction in errors and cut training time by half, significantly boosting operational output. Education is undergoing a paradigm shift toward immersion learning. Students now use spatial computing to turn abstract concepts into tangible 3D experiences. In history classes, students can walk through reconstructed ancient sites, examining architectural details in real scale as if they were physically present. In science, students interact with complex molecular structures in mid-air, manipulating bonds and geometry to understand chemical interactions firsthand. By making the intangible tangible, immersion learning allows students to grasp complex spatial and temporal topics with unprecedented depth and speed. By mid-2026, the extended reality landscape has fundamentally shifted. For the first time, revenue from AR smart glasses has surpassed that of dedicated VR headsets. This crossover signals a move away from niche, bulky headsets toward mobile, everyday spatial computing that integrates seamlessly into our daily lives. We are witnessing the final chapter of the smartphone era. By 2030, the portable screen will transition from being our primary digital hub to a secondary auxiliary device. Spatial glasses are set to become the central point of all digital interaction. These devices map our environment, allowing information to overlay reality seamlessly. As spatial computing matures, the physical constraints of 2D displays disappear. The future is an interface that exists everywhere, anchored to the world around us. The era of looking down at our palms is coming to an end. A new immersive reality awaits. The most significant hurdle for spatial computing is the privacy of our physical environment. To function, XR devices must map our private spaces in high resolution. This process creates a digital map of your home, capturing layouts, personal belongings, and even your daily movement patterns. This data is sensitive. Spatial data privacy is now the most critical regulatory hurdle. Manufacturers must ensure this data remains local, secure, and beyond the reach of unauthorized access. Virtual reality and augmented reality represent two distinct paths in spatial computing. Virtual reality is designed for total immersion. It effectively closes off the physical world to transport the user into a purely digital environment. Conversely, augmented reality focuses on augmentation. It keeps the user grounded in the real world while overlaying meaningful digital information. The core difference is simple. VR is about isolation to achieve immersion, while AR is about integration to achieve augmentation. The boundary between our physical world and digital data is rapidly disappearing. XR is evolving. What began as a platform for gaming is now becoming an essential professional tool for the modern age. By blending spatial awareness with real-time data, we are moving toward a future where computing is no longer a screen we look at, but a world we inhabit.